Hello everyone, I am Bekir Bartu Cebeci and this is our Physics 212 project about the cathode ray tube experiment and oscilloscope implementation. Our project explores the physics and engineering behind cathode ray tubes, devices that were once the backbone of TVs and oscilloscopes. CRTs operate by emitting a focused electron beam in a vacuum. This beam is steered by electromagnetic fields generated by solenoids, and when it hits a phosphorescent screen, it creates visible light. We began by dismantling a CRT television and safely discharging its high voltage capacitor. There are two solenoids inside the CRT, one for vertical and one for horizontal deflection. Then we ran experiments to understand how the electron beam behaves under varying magnetic fields. Using signal generators, we were able to deflect the beam and display some simple shapes on the screen like the circle seen. Then, to draw some arbitrary shapes, we used an odd amplifier to amplify the current we give to the deflection coils. We wrote a Python program to display some more complicated shapes like a cardioid, a star, and a flower, which are kinds of spirographs. After that, we tried to draw a word on the screen. We drew the word honor on the screen. However, because odd amplifier alters the voltage function we input, the word seems distorted. Then an oscilloscope is built by implementing the signal generators. An oscilloscope is a laboratory instrument commonly used to display and analyze the waveform of electronic signals. For the vertical side, a ramp function is inputted, and for the horizontal side, the signal that wants to be visualized is inputted. If the frequency is an integer multiple of each other, then the signal is displayed stationary. For experimentation, we observe the deflection distance compared to current given to solenoids. For some current values, distance is measured and they are plotted with the theoretical graph. The linear trend line is observed as expected. Then, an external magnet is used to deflect the electron beam, and its distance to the TV is compared with the deflection distance. The data is plotted with theoretical graph and the expected asymptotical behavior is observed. After that, some calculations about relativistic effects are done. Since the electron beam is moving with about 8% of the speed of light, there are some notable changes in its physical quantities, like the mass, momentum, energy, or the length and the time the electron experiences. Also, some experiments about the electron emission from the cathode metal and absorption of electron on the screen are conducted. The metal is heated and given voltage to emit electrons, and the current of the electron beam depends on its temperature, cross-section area, and type of metal. The work function of the metal is calculated with this equation, and the work function is found to be close to the tungsten's work function is expected. The emission of light on the screen is due to a phenomenon called phosphorescence. The brightness of the screen depends on the area illuminated, the power of the electron beam, the wavelength of the light emitted, and the efficiency of the system. The brightness is calculated theoretically with this formula. Also, with a mobile application, the brightness of the screen is measured close to the theoretical value. To conclude, this project blends experimental physics with modern electronics. By simulating, manipulating, and visualizing electron behavior, we gained hands-on insight into CRT technologies. Thank you for watching.